Alright, so this is a video lecture on Orifice Sizing for instrumentation systems at Red Deer College in the IET program. We're talking about Orifice Sizing here. So referring to the PowerPoint here on slide 3, the first kind of slide where we're getting into it, we're talking here about the procedure for sizing for this beta naught here, the first calculation at beta. So the procedure to do that is, first off, we need to know the flow rate we're going to expect, the line size, and our differential pressure here. So we need to know those conditions, the conditions of our process, and then from those conditions, we can then figure out the flow rate that we're going to use for sizing. So to do that, we multiply by 0.8 here. We need to first know what kind of our maximum flow rate is going to be. So it says here to multiply upper range value for flow rate by point. So we use 80% of our max flow. And then for our differential pressure, the maximum differential pressure that we're going to expect, we take that and multiply it by 0.64. And then use those values in all subsequent equations here. So some of the other things that we need to know is the density of the fluid, the viscosity, and also the Reynolds number here. And once we have all that information, then we can go on and figure out this SM factor, which is is our sizing meter factor. We use that then to calculate our beta naught there, our original beta value that we need. And then from that we can figure out, once we know beta, we would have known our line size here from the beginning, and we know that beta is just a simple small d over big D, small d being the orifice bore, and the big D being the line size. So if we know the line size and we know beta, then we could figure out what our orifice plate size should be. So the diameter of our orifice. So this is kind of a quick overview of what needs to be done. So there's going to be some new things here, but there's also going to be some things that hopefully you recognize from Miller's equations, because this whole procedure is from Miller's handbook, the flow engineering handbook produced by Miller's. There's going to be definitely some calculations I hope that you recognize. One of the new ones is going to be this SM factor. That's going to be new, but we'll see that coming up here. So on the next slide here, this stuff we should recognize. This stuff is thermal expansion factors correcting for the little d and big D for the orifice diameter and the inside pipe diameter. So I'm not going to go into too much detail here, but these calculations we used in process measurements 3. So just keeping in mind what the difference between D is here, the actual D here, this is at flowing conditions, and then down over here there's the measured, which is at 20 degrees. That's the size of it when it was measured at about room temperature, 20 degrees C. Did I go ahead? No, there we go. So the next one is Reynolds number. Once again, should be fairly straightforward. We've seen this before as well. So yeah, this I'm not going to go into much detail here. We need to know Reynolds number for sizing our orifice plate. And this slide here is just showing how we can take the formula from the previous slide over here, where we're using average velocity, and make it easier, because usually when we said one of the variables that we want to know is the flow rate, and that's what this is manipulated down so that we can use mass flow. There we go. Our mass flow rate right there, which is this guy right here. So it's been manipulated so we can just plug mass flow rate right into it, and if we know the internal pipe diameter and the absolute viscosity here, we can quickly calculate the Reynolds number. Over here is that new SM factor. and it's talking here where it's derived from. It's derived from the fundamental mass flow equation here that we would have seen in process measurements 3. So the thing that's highlighted here in red, this is where it's derived from. So you can see how, maybe I'll just undo my marks there. You can see we're going from here to here, and you can see that it's been manipulated. And this portion that's highlighted here in red is what's down in our SM factor there. And then we go ahead and tag on our discharge coefficient C and Y there as well. The discharge coefficient and Y, which is the expansion coefficient. So you can see now how the fundamental equation then simplifies, and that's where SM would fit in, is right here in our equation. So if we bring that and take that and manipulate that to solve for that SM value, you can see we go down to here and it's been manipulated. If we know our mass flow rate and differential pressure, our density, and the inside pipe diameter here, we can figure out our sizing factor here. So we need that sizing factor to size for our orifice plate. We'll see where that plugs in later on here. But that's what the sizing factor is. That's where it comes from. So this formula up here is hopefully something that we've seen before, because that's now kind of shows you where the SM factor comes from. And now over here, we can take that SM factor right here, and we can use it. We can rearrange it to solve for beta, because that's what we're after right now. We're going for our beta naught here, and so you can see how it has been rearranged down here now to solve for that. And SM is now plugged in right here. So the value over here, SM, that I underlined right there, would be coming from all of this, would be plugging in right here. And then that would be we'd be able to solve for beta here. So to start things off, to solve for beta back over here, we need to give ourselves a starting point. So, and to do that, this equation is kind of the base equation here to figure out our discharge coefficient. Because, so you can see that there's these two values, K1 and K2, that are here. Those are two constants, but they'll be different for the type of meter run that you're working with. To figure out our first approximation here, we're going to need to know this C value here, and which is the discharge coefficient. It can be approximated if we know the sizing factor that we calculated in the slides from before. And you can see that if we go back over here, our first approximation here at C, we need to know that, and that's what this formula right here is giving us. And so K1 and K2, you're going to see in the slides coming up, are going to be different depending on the type of meter run you're using. So if we're using our typical flange tap meter run, it's going to have certain constants. If we're using a one that's there's some other fittings, I guess when we get there we'll see, but the flange tap is the most common, where we have 1 inch, our taps are 1 inch upstream and downstream of the orifice plate, faces of the orifice plate. So what's being shown down here now is they went and substituted this here in right down here, and they've said that the Y value is equal to 1. That's what that's showing. It's kind of, for some reason, kind of subscript or down lower, but that's supposed to be Y, and then all of this here is our C value. And if I just go back to the slide here, there's Y as well. So this formula right here is being used right here, and we've substituted those values in to get our first approximation, because that's what That's what beta naught here is, to get us our first approximation. So the slides coming up are going to give us these values here that we're missing. The sizing factor, we know how to figure that out. We've derived that from our fundamental equation for mass flow. And then these two here are going to be specific to the type of meter run that we're going to be using. And the one that we're going to be typically or always using is going to be, in all of our examples, is a flanged tap fitting. And so the depending on our Reynolds number here, if it's less than 200,000 and greater than 10,000, we use this equation here, and if it's greater than 200,000, then we use this equation here. So when we calculated our Reynolds number that beforehand, this would decide which equation that we would use here. So what this is saying now is to solve for beta, the actual true beta value here, because before we were just talking about beta naught, our first attempt, is we need to do iterations, because this value here and this value here, they depend on the beta value. So when we do our first estimate, calculate our beta value here, calculate this, these values are going to go back and change because we bring this back around here, plug them in, and the C and Y value, discharge coefficient and expansion factor, they're going to change, and they're going to change our beta. So we have to do this iteration to get a very precise value, if we want to have a precise value of what our beta should be here. So that's what this is talking about. Now the procedure for that, we calculate our beta naught, is kind of what we were describing. Select a discharge coefficient, C, for the primary device, and iterate to obtain successive values for beta. So we substitute beta naught first initially into the discharge coefficient. That would be our C value. Set the gas expansion factor to 1 for liquids, but if we weren't using liquids, we would then use the Y calculations for that, which is also beta dependent. And we keep iterating until beta changes by less than 0.0001. So after we're done that, we can then calculate the bore of the primary element, which is our orifice plate. So some equations that should be, well, maybe not familiar, but they're big, and you maybe recognize them slightly because we've used them in process measurements 3 as well, is the ones for our discharge coefficient here. And you can see that they're dependent on beta here, and that's why it makes it an iterative solution where you have to keep kind of going in a circle until it stops changing. So it says up here in the turbulent flow regime, greater than 4,000 for a Reynolds number, the discharge coefficient for flange, tapped, orifice meter runs can be expressed as, if the inside pipe diameter is greater than 58.4 millimeters, we use this equation. If it's between 50.8, or roughly 2 inches, and if it's above that or less than 58.2 millimeters, then we use this equation. So when we were programming our program for this in our calculators, there probably was an if statement on which one of these to pick, and that's why we need to calculate the Reynolds number first before we choose which one we're going to do. And for our Y values here, if it was a gas that we're working with, we would need to know where the pressure is being measured, if it's upstream or downstream, and that would then select the correct Y value to use, so that we can figure out what our beta value is going to be through that iterative solution there. So these should be also, hopefully the gas expansion factor isn't a brand new thing. It should be, it was used in process measurements 3 as well. So here, this is the final equation at the end. After we've solved for beta here, and we know our D value here, because that's we're going to know the size of inside diameter of the pipe that we're using, and the thermal expansion factor of our plate. Those 3 variables get plugged in to figure out D measured at 20 degrees. So that's kind of our final step after we've done the iterations. So that's what we're going for. We're going for measuring what this demeasured value should be at 20 degrees C. The reason why this is down here is because this other stuff is going to be at flowing conditions. Oops, yeah, flowing doesn't really show up that well, but flowing conditions, and this here would be at our 20 degrees C here. So that's going to correct for. So this here is kind of our step-by-step process, and it should mimic quite similar to what I talked about. We should see some of the values here, like initially when we're estimating the differential pressure that we're going to be using and the flow rate that we're going to be using. We're taking 80%, 64% with the differential pressure. So this stuff up here is, we use this in valve sizing as well for dealing with a gas or liquid. So we can make sure we find our mass flow. We're going to start with mass flow. Figure out our maximum differential pressure that we can have. And when we figure out the maximum differential pressure, we can then apply this calculation here, because this is going to tell us what our maximum pressure needs to be. And then here in step 3, we need to select the range of our measuring device that's going to measure the differential pressure, most common being 25 kPa right here. So if dP max is let's say it's 30, then we can select 25 here. But if it was less than that, then we'd have to look at a smaller range, like maybe the 12.5 kPa range. So these are standard ranges here, right? And we're after that upper range value for figuring out our dP value that we're going to be using, because we're going to use 64 or 0.64 of that upper range value. So we need to know what our range limits are going to be for our device. This tells us what our max can be here, and this here is the one we pick. We got to pick a standard range here. We can't just order one, because we might not be able to order one that's, say, 30, or if we calculated this to be 32.3, you would go after a standard size. You wouldn't ask a manufacturer to produce something custom for you, right? So that's what's happening there. Here's that SM value that we talked about in the presentation, right? And this is our Reynolds number. Whoever made the procedure here kind of, instead of, we think it was called capital RE in our slides from Miller's, but someone slightly modified it here. And then there's our beta naught there as well. So that's what this procedure is. It's mimicking just what we talked about. And the next page on the procedure here down, you can see there's the Reynolds number we talked about here. It's talking about if it's less than 200,000, and it's talking about our K values, our constant values. And we talked about this equation here too for beta naught. So once beta naught's figured out, then it starts figuring out our discharge coefficient here, because we need that, you can see, for these equations, right? And we talked about the different sizes and stuff as well here. I'll go to the next slide. And then if it's a gas, you can see we have to calculate it. If it's a liquid, we just use 1. And then here we determine the new beta value, right? And from that, we take these values and go back up to here to step 10. And it's talking about recalculating. This is for something different. So we come back up to step 10 here, and we keep doing that until our value doesn't change any more than 0.001. And then at the end, we can solve for our beta value here. It looks like, I think they're correcting for, they're making a correction, looks like here, for our plate, so we get the measured value, because they don't show it here. But okay, so that's our procedure for going through. We've programmed this into our calculator, we've tested it, And now what I wanted to do is go through an example on sizing an orifice plate. So right here we've got a data sheet, instrument data sheet here on a device that we're going to be sizing for. I put some notes down here when I did this in class. They didn't state the pressure tap location or the expansion factors, and those are for the orifice and pipe. Orifice and pipe. So what I want to do now is have you grab your calculator, and we're going to open up the orifice plate sizing program. So just getting to it, orifice size. We titled it orifice size. I'll just write that up here. Orifice size. So that's the name of the program in the calculator if you programmed the example that I posted on Blackboard. And the first thing that it asks is for our maximum flow rate. So in this example, we have other examples where maximum flow rate will be listed, but you can see here there's nothing there. It gives the normal flow rate. So we know that the flow rate needs to be, for one, my calculator right now is asking for the flow rate in kilograms per hour, and this is in liters per second. So we need to make sure we divide by 1,000 to put it in meters cubed per second, and then multiply by 3,600 to get it into meters cubed per hour, and then multiply by our density, which is going to be 1,000 times 0.778. So we've got a few things to do to tweak that. So what I'm actually going to do is exit on my program for the moment and make that calculation so I can write it up here. And the other thing that we need to apply is, since it's the maximum flow rate that our calculator is asking for, and this is the normal, we're actually going to have to divide by 0.8 to figure out what our maximum flow rate is, because our program is going to multiply by that 0.8, so we need to divide it. But I'm going to key this in right now. We've got 100 liters per second divided by 1,000 liters in a meter cubed, multiplied by 3,600 seconds in an hour, and also need to multiply by our density of 778 kilograms per meter cubed, and then I need to divide by 0.8, so I get a value of 350,100 kilograms per hour. And that's with applying this factor right here. So that's what we're going to need to key into our program. So I'm going to go back to my program. And key this in 350,000, 100 kilograms per hour. The density it's asking me for now is 778 kilograms per meter cubed, and line pressure, we can look that up here on our data sheet. It is 700 kPa gauge, and our calculator is asking for it in absolute pressure, so we need to add those two values, so 795. And our viscosity here, and I wanted to highlight this because I actually had an error, and I wanted to point this out right now. Viscosity, the program was, all the formulas were written assuming it was Pascal seconds, not millipascal seconds. So you might want to go into your program and tweak that so when it asks you for it, to ask you for it in Pascal seconds. That'd probably be the simplest thing here, because you might cause confusion, because I think I noticed when I was starting to prep for this video that it was asking for millipascal seconds, so you want to change that. I've changed mine already. It says Pascal seconds, and that value that's given to us is in millipascal, so we need to enter 30 and then divide by 1,000, because it's going to be 1 millipascal second is 1,000th of a Pascal second, so 30 divided by 1,000, and it gives us a DP max of 26.5. So my first output is DP equals 26.5 kPa. So we need to select a standard range, like we pointed out on that procedure sheet. And the standard range we're going with here is 25 kPa. So we key in 25 kPa for the DP. The DP selected is 25 is what I'm keying in. And that's kPa. And now it's asking for our pipe, inside pipe diameter. And to simplify things, since I don't have my book with me, if I don't, on any test or exam, if I don't state the inside diameter, just use the measurement given. So 10 inch, schedule 40, and our program's asking for it in millimeters. So we need to multiply by 25.4, so 10 times 25.4, which is going to be 254 millimeters. We key that in, and it gives me a DP norm of 16. So this here value, the DP norm value, is going to be 25. The 25 here multiplied by 0.64 is going to give me this norm value. Then it has our SM value, that sizing factor, and that's given. Its SM is equal to 0.3077212548, and my Reynolds number NR is equal to 12,999.74233. Then I press enter again, and it gives me my beta value, 0.6674305743. And now it's asking me for my expansion factor, and that's what I was talking about down here. They weren't given. So for us, what we're going to be using, unless it's on an exam, I would give this to you or I would state it. But since it's not shown anywhere on this data sheet, not that I could find anywhere, the one that we're going to be using for the orifice plate, since it's stainless steel, you can see up here, it's going to be, I'll just write it over here. Actually, I'll write it up there. 1.1 times 10 to the negative fifth for our orifice. And for the pipe, I'll write that one down over here. 1.6 times 10 to the negative fifth is the value we're going to be entering in for that. So for the plate, the PL, 1.1 to the negative 6, and for the pipe, 1.6 to the negative 5. Shoot, I just entered in my, I'm just going to pause this, I entered in my plate wrong. There, sorry, I had to fix something. So I've entered in my plate size, my pipe, at 1.1 times 10 to the negative fifth for my plate, 1.6 times 10 to the negative fifth for my piping, and the temperature should be given on here. It's 100 degrees C, right there. So enter 100 degrees C because it's asking for units of Celsius, and then it asks you if it's a liquid or gas. And on this side here, we're dealing with a liquid. It's light oil. So enter 1 in for it to say yes to that, and then it gives me a C value equals 0.630642895, and FA of 1.001561949, and the y is of course equal to 1 because it's a liquid. And then our beta here is equal to 0.661797005. And then it asks us if we want to iterate again. So what I'm going to do is I'm going to iterate this, and I'm going to keep iterating it until it stops changing. So I got, let's do this until it stops changing. My beta value. Beta value is still changing, it appears. There, so I went until it stopped, and so my final beta value here was equal to 0.6619603.896. That's the final. Let's do one more to make sure. Yeah, so that's what it is. So now we take this value here and manipulate our formula, little d over big D, and we multiply these two values together. So our piping diameter there was, so what I should do, our program should store this, it should once we say no, so I'm going to say 0 to iteration, it's going to stop, and now what I'm going to do is it stores it in alpha key B for beta, just double check, yeah, that's stored there. And so now I need to just multiply that by 10 inches times 24.5, and so I get a orifice size, our little d, this is kind of our final answer, is 168.137939 millimeters. So that's our orifice plate size approximately. Orifice plates also come in standard size, so we're going to be picking one closest to that value. So we've got the first one done here. We've sized our liquid orifice plate. So now what I want to do is go and size this plate over here. So I'm going to clear this. I should be able to press a button here to clear this. Oh, yes, I'll have to bring in that picture again here, sorry. There, okay. So now we're after the second question here, where we have, now we have a gas. So we're going to be sizing for a gas. So I'm going to open up my orifice plate program here again. Oh, wait, actually, what we need to do is we need to figure out our, what's our mass flow rate going to be here. So we need to use, let's clear this as well and bring that back in. Yeah, so what we're after here now is figuring out our QM here for our gas. So let's just have a quick look. So this here is our normal flow rate. It's in standard meters cubed per second. So we're going to need to know the density to get this into a mass flow. So let's, to get our density, we need, since we're going after the standard calculation here, right, because it's given it a standard flow rate. So we'll need this equation right here to do that. So we have our molar mass and our atmospheric pressure at standard conditions. So I should be able to bring that formula over and figure that out. Yes, so I'm just going to write that down here. Density at standard conditions is equal to 101.325 times m over 1. I don't think there's a z value given here. Compressibility. Oh, there is a compressibility factor. But you know what? We don't need that right now because I'm just going to get rid of that. We don't need that because at standard conditions, it should be a value of 1. This would be at flowing conditions. So if we wanted the density at flowing conditions, which we will need that as well. And then we multiply it by 8.315. And then our absolute temperature. Let's just see what our temperature is. It's 30 degrees. So it's going to be 30 plus 273.15 Kelvin. So we need to enter that in and figure that out. Molar mass is given right here, 16.043. So 101.325 times 16.043. And then I need to divide by 8.314. I think that's a 4. We're supposed to be doing 4 here. And multiplying by 303. So 273 plus 30, 303.15. So standard, I get a density of 0.6449627.064 for our density, kilograms per meter cubed. But now we need to go and also figure out the density at flowing conditions. So let's grab that as well. We need this here. So we need the absolute pressure times the molar mass times our Z at flowing conditions, which is given, and our temperature at flowing conditions. And I just realized we made a mistake. Uh-oh. Okay, yeah, this here should have been 15 right here, not 30. So that's going to change this. Good thing I caught that now. So let's change that. So if I multiply by 303.15 and then divide by the right temperature, which would be 288.15. So this actually should be 0.678537.027. There. Okay, and now our density over here, we need to figure out, we need to take our absolute pressure, which is, we've got 95 kPa, and the flowing pressure, which is 12,000. So we need the 12,000. It'll be 12,095 kPa multiplied by that molar mass, which was 16.043, all over our Z value, which is 0.7884, which I got from right there, and our relative gas constant 8.314, and then our temperature, the correct temperature now, because this is at 30 degrees C, it's at flowing conditions, which is 303.15 Kelvin. So we enter that in, and that's going to give us our density, because we'll need the density at flowing conditions as well. So 12,095 times 16.043 divided by 3.7884 times 8.314 times 303.15. And at flowing conditions, we're at 97.65. 112429 kilograms per meter cubed. So we've got our values. Let's just have a quick peek here. We should be able to start running our program now. So I'm going to go to the Orifice Sizing program in my calculator. And it's asking me right away for my maximum flow. And of course, here once again, this is a normal flow. So we're going to, when we enter this in, our flow rate, it's going to need to be the maximum flow rate, right? So to figure this out, we need to multiply that flow rate by our density here. So I'm going to go ahead and do that. I got to exit of my program. I jumped into it a little early again. So 11.318. This is in standard meters cubed per second. This is in standard conditions here. It's kilograms per meter cubed. So we multiply by that value to give us kilograms per second. So multiply by 0.678537027. And then I get 7.67. I need to put this in kilograms per hour. So multiply by 3600. And so what I end up with is 27,646. And that's going to be normal flow. So I need to divide by 0.8. And I get 34,558.56932. This is now in kilograms per hour for us. Kilograms per hour. So we need that value to enter into our equation. So now I should be able to go back to my Orifice Sizing equation and enter this in 34,558.56932. Enter that in. Density is the flowing density, this one over here, which is 97.65112.429. So I'm keying these all in. Normally I would probably try to store them in alphanumeric character, but we got those keyed in now. And the line pressure it's asking me for now in absolute, and that was given right down here. So this is 12,095 kPa absolute. And the viscosity here, it's kind of hard to see, but it's right there, 0.011, and that's doesn't give us the units. Let's just have a quick check here. I might have, I'm going to assume that it's in millipascal seconds. Yep, it's in millipascal seconds. It's not showing there, but it should be. So that means you need to take 0.011 and divide it by 1,000. So now I get a maximum kPa value. So where should I write this? This is dP max equals 403.16667 for our dP max. So for our dP selected now, we can pick really anything we want, but I plan to just use our normal 25 kPa. It's pretty standard for most differential pressure cells or differential pressure transmitters out there. 25 kPa is pretty standard, so we're going to pick 25. So we'll just write that down. dP selected equals 25. And then my piping, it's 12 inch this time around. So 12 times 25.4. And I get a dP normal. And this will always be dependent on the dP selected. dP norm equals 16. SM, sizing factor, equals 0.0595401359. And the Reynolds number my calculator gives me is pretty big. Let's see, 2,916,390.749. And our beta here equals 0.3142428,163. And now it's asking me for my expansion coefficient, and they use stainless steel up here again. So that was 1.1 times 10 to the negative fifth. And our piping is carbon steel, which I don't think it's showing here, but the one for carbon steel that we used in the last example as well is 1.6 to the negative fifth, times 10 to the negative fifth. Temperature for this gas is at 30 degrees. Yep, right up here. So let's put that to 30 degrees. And the liquid, it's not a liquid, so we put 0 in. And now it's asking me for some new stuff here that we didn't get last time. It's asking me for my K value. So what I'm going to do is I'm going to clear this because I don't think we're going to need any more of these values. Just so we can... Oh yeah, I forgot it does that. Let's bring our example back in. Okay, yeah, so that K value, I wanted to point that out. It's a heat capacity at constant pressure over constant volume, which is our K value right here. So sometimes it's given that way, CP, specific heat over specific heat at a constant pressure, that's what CP is, over specific heat at a constant volume, which is what K is. And so that value is this 1.3 value here. So 1.3. So it could be given as either K or as this value. Likely on my tests and exams it'll be a K value. And the pressure, is it upstream or downstream? And in our case we're going to assume that it's, I don't think there's any information here that gives us, if it stated like P1 for the line pressure, that'd be upstream, P2 would be downstream. Just looking, taps flanged. Yeah, I don't see anywhere. We're going to assume it's upstream. Doesn't look like they state anywhere, which is too bad. It should be shown here somewhere. Yeah, I don't see it anywhere. Okay, so yes, this is what we're going with P1, and so that means that this pressure right here measured is upstream. This should be a P1 right here to tell us that information. So P1, and the pressure is upstream, so we're going to go 1 for yes on our calculator, pressure up. And then now it spits out some values here. So we have our C value, our discharge coefficient, at 0.5986133865. FA 1.00021. 0.9015, and then our y 0.9995793,171. Press enter, and it gives us a beta value here of 0.3146344,318. And it's asking if we want to iterate. We're going to go yes. And we're going to keep doing it until it stops changing. So there, my final beta value, 0.3146326,073. And then we need to multiply that by our pipe diameter, which is 12-inch. So for a little d, I'm just going to exit out of my program. Alpha b times 12 times 25.4. So I get 95.9001869 millimeters at the 595 for our orifice plate. So we want to pick something close to that for our orifice plate, obviously. And yeah, so that gives us two examples here, the liquid and the gas example there. So hopefully that answers any questions on the orifice plate sizing. The other thing that I will post on Blackboard is a sheet that shows the data sheet that you will have to record your answers in on the final exam, because there will be an orifice plate sizing question on the final exam. So hopefully this helps, hopefully this makes sense, and you can work out any issues with your program. This would kind of test it all, and it also shows you where to find all the information that you need to enter into your calculator. So yeah, if there's any questions, please contact me on this. Thanks.